Welcome back, ladies and gentlemen. Today we're going to talk about section 8.5. We're on day one. We're going to talk about trapezoids. This section is about trapezoids and kites. We're going to divide it up into 2 days, one day talking about trapezoids, one day talking about kites. On the screen, you'll see your exit question at the end of this lesson. Okay, let's start off with the definition. First off, trapezoid. We're going to define it. The official definition is a quadrilateral with exactly one pair of parallel sides. I would also take a moment to pause the video and draw this drawing. Even though a quadrilateral only, or a trapezoid only has 4 sides, it has a lot of little parts to it. Okay, first off, you have exactly one pair of parallel sides, and those sides have special names. They are called bases. And the bases are parallel to each other, and they are also of different lengths, but kind of by definition. If they were the same length, then you would have a parallelogram. Then you've got the two sides that are not parallel to each other, and those are called legs. In addition to that, you have base angles, which are associated with a base. So the two angles that touch a base are collectively called a pair of base angles, and here's the other set of base angles. So there's two pairs of base angles going on inside of a single trapezoid. Next definition we have is that of an isosceles trapezoid. So you just take an isosceles, or you take a trapezoid, and you make the two legs congruent in length, and you have yourself a isosceles trapezoid. There's a picture if you want one. Then we can also do a mid-segment of a trapezoid. We've done mid-segments of triangles. This is what it looks like when you do it to a trapezoid. You find the mid-points of each leg, connect them with a segment, and there you have constructed a mid-segment of a trapezoid. There's another way to draw a mid-segment of a trapezoid by finding the midpoint of the two bases, but when we refer to the mid-segment of a trapezoid, we are referring to the mid-segment that is formed by finding the midpoint of the legs, not the bases. So slight distinction there to be aware of. Next, as you can guess, we have a number of theorems. The first one is about an isosceles trapezoid. So basically it says that if you have an isosceles trapezoid, that is that the legs are congruent, then the base angles are also congruent. So the two pairs of base angles, the two angles that touch the same base are congruent to each other, and the two angles up here that touch the same base are congruent to each other. This is really, really similar to the base angles theorem that we had about triangles. And just like that one had a converse, so does this one. So theorem 8.15 simply says that if you have congruent base angles, then you have an isosceles triangle. That is, its legs are the same length. Please, please, please use these correctly. Make sure that you understand which direction these flow. This one is going forwards in the conditional way. This one's going backwards in the converse way. And then to complicate things a little bit further, then we have a theorem 8.16, which is very important. You're probably going to use it more, and it is an if and only if, a biconditional. So this one works both directions. And it says that if you have an isosceles triangle, or an isosceles triangle is isosceles if and only if its diagonals are congruent. So basically that means that you can say, oh, I've got an isosceles triangle, therefore my diagonals ought to be congruent. And it also says that if you've got a trapezoid with congruent diagonals, then it is automatically an isosceles triangle. So this one you can use both ways. The previous two were unidirectional. And the final theorem we have for today is the Midsegment Theorem. And the major portion or the most interesting information from this theorem is that you actually get a formula out of it, and you can imagine that a lot of your problems will feed off of you being able to set up an equation like this. And the unique thing about a midsegment of a trapezoid, it is if you added up the length of AB and DC and took the average of them, MN is the average length of AB and DC. So in other words, take AB plus DC and divide by 2, and you'll get the distance of the midsegment. Just like in triangles, it is parallel to the base of the trapezoid, and since that base is also parallel to the other base, all three segments there are parallel to each other. So kind of a lot going on there. It won't be referenced too often, but very good to know about. Okay, let's do an example. This first example says show that RSTO is a trapezoid, but not a parallelogram. So you need to show that it fits the definition of a trapezoid and not a parallelogram. See if you can figure out how you would do that. Pause the video and come back to me. So here we have a quadrilateral graphed on a coordinate grid, so we're able to perform calculations. And we need to make it fit the definition of a trapezoid, that is exactly one pair of parallel lines, and not fit the definition for a parallelogram, that is two pairs of parallel sides. So basically, we need to show that this base is parallel to this base, and this line right here is not parallel to that side. And we're going to do that through slopes. So all you have to do is go through and calculate these slopes just by counting squares if you want, or you can use a slope formula to find the slopes of each of those four segments. When you do that, you get these results, and you'll find that the slope of RS is 1/2 and the slope of OT is 1/2. Hey, those are the same, therefore they're parallel. And then you've got the slope of RO, which is actually vertical, so we'll call that an undefined slope, and the slope of ST is -1, which are obviously very different from each other and therefore not parallel. So therefore, this shape has exactly one pair of parallel sides, but not two, and therefore is a trapezoid, but not a parallelogram. The next example I have for us is more of a higher level problem, but you can certainly tackle this. Will I be crazy enough to ask you to do this on a test? Maybe. I could see that happening. It wouldn't be the most outlandish thing to ask for in a 4-level problem. So we have a trapezoid plotted on a coordinate grid, but we're not given any numbers. And your job is to show that that is not only a trapezoid, but also an isosceles trapezoid. So think about how you would go about doing that. Pause the video and come back to. Okay, so we have to show that this is isosceles, and we can either show that the base angles are congruent, which would involve trigonometry, and we don't have any numbers to play with, so that would probably not work. I haven't played around with that. It might work, it should work, but it would be difficult. The other way to do it is to show that the diagonals are congruent in length, and I think that would be our best bet. So basically, we want to make sure that the diagonals of this trapezoid are the same length, so let's draw them in. So if we draw them in, we might as well throw some more labels in there, PQRS, and we want to show that PR is the same distance as QS. And we're going to do that using the distance formula, which is basically remember, just a fancy version of Pythagorean theorem. And what it does is that it finds the difference of the x values, squares them, adds them to the difference of the y values squared, and then takes the square root of the whole deal. We haven't talked about the distance formula for a while, so I thought I'd just do a quick rundown of that. So we want to show that the distance between P and R is the same distance between S and Q. So let's start plugging it in. Let's start with P and R. So if we start here and we find the difference of the x coordinates, we would take C minus -a. So we'd get C plus a inside this first term, and then we would square it. And then over here, we would take D minus b and square it. And it would look something exactly like that. And then we're hoping that SQ will work out to be exactly the same thing. But then you look at this and you say, oh, if I take C right here and subtract A, then I'm going to already have the opposite of C subtracting an A. But if I did, and then if I say, okay, well, let's just switch it so we get a positive C, A minus -C, but then we have B minus D instead of D minus B. So we got to fight a negative one way or another. It's got to equal it. We know it ought to. We just have to fight through it. So the way I'm going to set this up is with the first option where we still have a D minus B, but we're going to set it up with a -C minus A under the radical. And it looks like this. And you can see that the second half of the radical looks exactly identical to what we had in PR, so that's all good. But right here, we've got an extra negative hanging around, so we need to get this out of here. So we have to think about what this means right here. We have a binomial squared, which we're just going to take that chunk out of the radical and start playing with it. So a binomial squared, so it must be a binomial times itself. And if I have a binomial times itself, then I can FOIL. And if I FOIL, notice that everything is negative. So we're going to have negative times negative, negative times negative, negative times negative, negative times negative again. And so everything ends up being positive. Awesome. Now check this out. We can start recombining stuff, combine like terms. And then this is a perfect square binomial that has been FOILed. So this is a special case, and we can factor this back into c plus a squared. So we did all that work basically just to get out a negative so that we can make that term look exactly like this term. And now that it does look exactly like those two things, we can now say that these two distances are identical, and therefore the lengths of the diagonals are identical, and therefore by theorem 8.16 PQRS is an isosceles trapezoid. Here's your assignment and the details on how to do it the most awesomely. I'll see you next time.